recording. I'm gonna share my screen.
I have a question.
Yeah.
I know Monday is technically the last day of class, so we're not meeting that day.
No,
Oh,
I'm just gonna post the exam. You'll have all day to take it. You
okay.
can take it during class time, you can take it before, you can take it after, but of course, you'll have until 11:59 to finish it.
Okay.
Mhm. All right, so where we left off at was we were talking about chair conformations, and we're talking about the equilibrium, because these conformations are in equilibrium. It's just that the extent of equilibrium is what matters, right? So the more stable conformation, like I have shown, let's go back to this one with the tert-butyl group, right? The more stable conformation is going to be present in a higher amount, right? So there's actually a ratio between those two, and we can determine that ratio. We can determine it based on looking at the equation for the equilibrium constant. So let me put a page in, and we're going to talk about that. We'll keep this. So I'm just going to circle, not circle, but cut all this. All right. So we can look at this equation. And we can figure out the ratio based on this, like the ratio of conformers. Let's see, right? And this is delta G naught. So if I wanted to solve for KEQ, right? I need to divide both sides by minus RT. So that's natural log KEQ equals minus, over RT. And then I want to get rid of the natural log, which is base E, right? So KEQ equals E to the minus delta G over RT. All right, so this is the equation I can use to find the ratio of the conformers, right? And so let's take this and let me explain the terms. We're solving for KEQ, so we're looking for that. But these are numbers that we have, right? So we have delta G, which is the difference in energy between the two conformations. So between, I'm abbreviating that. All right, so the difference in energy between the conformations is delta G. R, we already know that from Chem. It's the gas constant. It's 8 point Russell. 8.314 joules per mole Kelvin. This is a kind of a sticking point because most of our energies are reported in kilojoules. So we got a choice. We can convert the energy into joules, or
bath time gets put on the aggressive breed list.
We can convert the energy into joules, or we can convert this into, excuse me, into kilojoules. So I always like to just turn this into kilojoules. So 0.08314 kilojoules per mole Kelvin. Because we need all those values to cancel. We need the kilojoules to cancel. We need the temperature to count, all this stuff to cancel, right? and the moles. All right, so then now we need, and then T is the temperature. But it has to be in Kelvin. All right. So in order to determine the ratio, this is the information we need. We have the gas constant. We just need the temperature because we have the delta G as well. What would delta G for this particular reaction be? Right. Delta G is just the difference in the energy between the two. So when one is 0 and the other one is 22,
What does that word say of after equilibrium?
ratios.
Um,
You're making fun of my R.
It didn't look like an R, sorry.
Yes, it did. Yes, it did. Don't play with me. Don't play with me. No, I'm just joking. Yeah, so this is delta G. It's just the difference in energy between the two conformations. So we know that, right? We just subtract them out, find the difference. So it's 22 kilojoules per mole, right? And there's no sign. Delta G is going to be positive. All right, so we're going to calculate this ratio. So we know delta G. What temperature do y'all want to use? Y'all want to use room temperature? You want to use a higher temperature, lower temperature? It doesn't really matter. Huh?
Room temp.
Room temperature. So at T is 25 degrees Celsius or what is that? 298 Kelvin, right? So T has to be in Kelvin. So 25 room temperature is 298 Kelvin. All right, because it's 25 plus 273. So we got everything we need. So let's plug those numbers into this equation. So delta G is 22 divided by 0.008314. Oh, hold up. Let me put my units in because that's important because I need everything to cancel. Because the equilibrium constant, the number is a unitless number, right? So KQ is this 22 and then 0.008314. Let me fix that for Tia said something else. Kilojoules per mole Kelvin. That's the gas constant times temperature, which is 298. Okay, so you can see all this stuff is going to cancel. The Kelvin is going to cancel. The kilojoules per mole are going to cancel. So you're left with a unitless number. And this is negative. And then this is E raised to that. All right. Somebody calculate that. Go ahead and the way I normally do this is just do the calculation first and then go back and save that number and then go back and do the exponent. That's my calculator. Right. So
I got negative 54.5.
okay, so let me see, times 298. You sure about that?
Yeah, I probably did it. I probably put it
It
in.
should be closer to like, it looks like it's gonna be closer to about 10 or 11. 2.7. So the bottom number is 2.477572, and the top number is 22. We divide that divided by 2.477572. It's 8. Hold up. Actually 8.797. Let's do that. 7. No, I'm sorry. 8.8797. And this number is negative. So it's going to be e to the minus 8 point. My eights, why they whooping my butt today? 1.8797. Did you get that when you redid it to you?
Mhm.
All right. I'm gonna put that in. I need to turn my phone sideways to get to the scientific calculator. Oh, hold up. I didn't put the negative sign in.
I got negative 7,184.
The number is negative.
Oh, you have to wait. The negative is on the exponent, right?
Yeah, it's on the exponent.
Okay.
I got 1.
0.00 what?
Oh, can you put it in scientific notation or
No, go ahead. What did you get?
0.00014?
Okay, that sounds about right. Let me put it in my.
Yeah, I got the same thing.
You said 0.00014.
Mm-hmm.
Yes.
Yep. One, 4. All right. So that number is my equilibrium constant. If I want to find a ratio, I could take that number and multiply by 100. And then what I get is going to be the lower number in the ratio. So let's do that. I'm running out of space. Hold up. Right. So if I multiply that by 100, what am I going to get? 0.014. Is that right? Is that right?
Yes.
So the ratio is going to be 99.086 to 0.014. That's how much of this isomer exists compared to the other one at room temperature.
I have a question.
Go ahead.
You got the 99 because we subtracted that from 100.
From
No,
100. Yeah,
the-
because this again, when I take KEQ and multiply by 100, I'm going to get the lower number in the ratio. So then I just subtract that from 100 because it's got to be a total of 100%.
Yeah.
All right, so whatever I get from that number from KEQ, if I take that and subtract it from 100, it'll give me the other part of the ratio. All right, let's do another one. Let's try this one with the bromine. Let's try that one. And we need to draw the chair flip too. So let's see. Let me add a page in down here. All right, so the first question is, what is the chair flip going to look like? Like, how do I get this in a more stable conformation where the bromine is actually equatorial? Because it doesn't matter how small the energy value is, it's still going to prefer to be in a lower energy state. We know the equilibrium is going to favor the equatorial chair. So what do I need to do to flip that chair? Is it going to be like this? Is that right?
Yeah.
Yes.
Yeah, there's always this carbon getting pushed up, and this carbon getting pushed down, like so. Right, so where's the bromine? The bromine is still on this carbon, and I didn't change the carbon, I just changed the orientation. So the bromine is going to be here.
I have a question.
Go ahead.
How do we know that the equilibrium or something favors the flip?
Because in the flip, the axial substituent is now equatorial. And that's always better in the case of cyclohexane. That's always better for your axial substituents to be equatorial, because you don't have the 1,3 diaxial interactions that you have here. Those are gone in the chair flip.
Okay.
So where each 1,3 diaxial interaction costs 1 kilojoule per mole for a total of 2 kilojoules per mole for that conformation, the ring flip is relatively zero. So it doesn't cost you anything for bromine to be equatorial. All right, so let's see so delta G in this case is going to be what? 2? Is that right? That's the difference between the two, right? One is 2, one is 0. So the difference is 2 kilojoules per mole. All right. So how do we calculate KEQ in this case? It's E to the minus delta G over RT, where delta G is 2, we know what R is, and let's take the temperature up some. Let's do it at 50 degrees. Let's say the temperature is at 50. So it's going to be 323 Kelvin. So let's just plug the numbers in and see what we get. See what the ratio is at that temperature. So this is 2.0. This is negative divided by 0.008 times 323. All right. Somebody put that in your fancy smancy calculator and see what you get.
I got negative 0.745.
Okay. And then what about what do we get after putting that in with the inverse?
0.475.
Say that again.
0.475.
We said 475.
Mm-hmm.
Okay. So you can already see it's going to be a huge difference in the equilibrium, because it doesn't cost as much for that bromine to be axial, right? It's 2 kilojoules. It's even though it's an increase in energy. It's not so detrimental that none of that exists at this temperature. So let's see what we got. So if I take KEQ times 100, that's going to give me 47.5. Right, so that's the low number in the ratio. So the ratio of at 50 degrees, my brain's moving faster than my finger, is 52.5 to 47.5. Right, so the 52.5 is going to be here. Right, so that's not that much of a difference at higher temperature either. That's not that much of a difference at all. Questions about this?
Was it, can you go down? So the ratio for the flip chair comes first always?
No, that's actually the lower number. So the higher energy, the ratio for the higher energy one, that's what we're going to get by taking KEQ and multiplying it by 100. It's going to be the lower number, basically the denominator, because remember, KEQ is products over reactants. Right, so it's when you apply this method, you're always going to get a smaller number first.
I guess I have the same question, I guess, relating to Tia.
Go ahead.
So I understand you multiply whatever you get for KQ times
100.
So I get after that you subtracted the whatever answer you get from 100.
Yes.
Okay.
And it'll give you the other part of the rate because the ratio is based on 100%.
Okay.
So you just subtract it out. And this is not you're not going to find this method in the book. It's something that I developed so that, we could take this and make it make sense.
Okay.
Not the KEQ part. That equation is already known, but I mean like figuring out the ratio after we get KEQ.
Okay.
Yeah.
So why how do you know what number goes to what? Yeah, I was confused on that.
Because, okay, let's think about it. We think about which one is more stable, which one is less stable. The more stable isomer is going to be present in a higher amount. So if one of them has an energy of 0 and one has an energy of 2 kilojoules per mole, the one that has the energy of 0 is going to be more stable. So there's going to be more of that present than the other.
Okay.
Right? The lower energy conformation is always going to be present in a higher amount. All right. Let me introduce another type of chair. We're going to talk about it for a second, and then that's actually going to be the last thing we discuss. I want to talk about a chair that's dot substituted. So let me go down to this page. So you can see here, there are multiple patterns, right? You can have 1,2's dot substitution, which is right here where the substituents are right next to each other. You can have 1,3 or 1,4. We're going to focus in on the 1,4 because those are the 1,3 is a little bit tricky to think about, and I don't want to rush it because especially since this being the last thing we talk about. So we're really going to just focus on 1,4 dot substituted cycloalkane. So this is, if you can see down here, like if it's dot substituted, right, you can have cis where both substituents are on the same face, or you can have trans where they're on opposite faces. And that's as a consequence of that, that also determines whether the substituents are axial or equatorial. So I have a table down here that talks about that. Where is it here? So if it's trans cis 1,4, you're gonna have one axial and one equatorial. If it's trans 1,4, then they're both going to be axial. All right, so we're gonna zoom in on one of those. We're gonna look at the trans 1,4, where both substituents are axial in one conformation. Actually, let's do the cis, because that'll give us a better. We could deal with the ratio. Talk about the ratio in more detail if we do the cis 1,4. So I'm gonna just grab this and put it up there on that blank page. Put that here and here. Copy this as well. All right, so depending on what the substituent is, that's going to determine like the energy. We already talked about that. And there are some substituents that are much higher in energy than others, like you saw, like with the tert-butyl, and then with the halogens. Halogens don't cost as much to be axial as a tert-butyl would. So I want to do, let's do cis. All right, so we're going to do cis, this molecule right here. And I'm opening up another window because I need the, yeah, here we go. I want to, I'm opening the window, another window, because I want the values for the groups. So yeah, so we know the tert-butyl is 11 for it to be axial, and then the phenyl is 6.3 to be axial. So let's draw this. It's going to be cis 1 tert-butyl 4 phenyl cyclohexane. All right. So for this chair, I'm gonna start here, and I'm gonna put the tert-butyl axial, and then I'm gonna put the phenyl equatorial. So the diaxial strain we're concerned with is for phenyl, that's 6.3 kilojoules per mole. And then tert-butyl, which is 11 kilojoules per mole. All right, and go ahead.
Did you have a table of those values? I remember you saying something about either be given or something.
Yeah, I'll give it to you on the exam, but let me do this. I need to copy that. Copy onto a blank document, and I can put this. I can actually put this in the chat because you can still see my iPad. Yes.
Yes.
All right, cool. Let me just I'm gonna actually put this Word document in the chat. So this is I need to add a row to it. Let me save it and I'm gonna upload it. Oh, hold up, I gotta close it. Try again. Learn something new every day. Didn't realize you couldn't upload it if it was open. Yeah, so I just uploaded, it's just a document with a table in it for the 1,3 diaxial values. All right, so we know phenyl is 6.3 and terbutyl is 11.0. I'm gonna have to move this down. What would the chair flip look like for this? What would I have to do?
The terbutyl
Yeah.
will become equatorial,
Mm-hmm.
right? And I forgot what it's called. The other one,
Phenyl.
the phenyl, will become axial.
Okay. But would the chair look the same or would it be different?
It'd be upside down.
Okay, I'll take that. You said upside down. Like that.
Yes.
It'll be inverted, right? This
Yeah.
carbon is going to get pushed down that way, and then this carbon is going to get pushed up that way. All right, so my terbutyl is now equatorial. And then my phenyl is now axial. All right, so where do the interactions come from that increase the energy? Where do those 1,3 diaxial interactions come from? Like what that make all the ruckus about something being axial versus being equatorial? I guess the question is, where are the other two axial sites on the bottom face? This is for terbutyl, this is the bottom face.
Oh, wait, I'm confused. Wait, I'm confused on what you're asking.
I'm asking where the other two axial sites on the bottom face.
Is it on the second orange dot to the left? Oh no, first one. Sorry.
Right, it's here. Because in order for it to be a 1,3 diaxial interaction, what that means is that if I start here as 1, that's 2, and that's 3 on the third carbon, that's another axial site. That's the same thing on the other side. Right, so both of these hydrogens are going to interact with that terbutyl group. So the total energy is 11 for one of them, but I got 2 axial hydrogens. It's going to be 22 kilojoules per mole. All right. Are we seeing that? Y'all seeing that? Questions about it? Go ahead.
So for that one we use the values for the terbutyl instead of
Because it's the tertiary butyl group that's axial. The phenyl group in this case is equatorial.
Okay.
You can only get a 1,3 diaxial for axial substituent.
Okay.
just like the same thing over here. Your other axial sites are going to be here and here.
Oh.
Yeah, I
Three,
guess.
three axial sites on the bottom and three on the top. Right, so now we're going to have interactions between these hydrogens and this phenyl group. It's both of them. So that's going to be 6.3 kilojoules per mole times 2, because there's always 2 axial hydrogens. All right, so what is that?
12.6.
12.6 kilojoules per mole. All right, are we good on that? So there's a couple of things that we learned that we're applying here. We're applying the fact that if something is axial and it's on the, it's an axial substituent, it's going to encounter these 1,3 diaxial interactions. And those interactions cost energy. And if we know the value, then we get 2 interactions. If we got one substituent that's axial, then you're going to have those 2 interactions. So it's always that the value times 2 in a scenario like this. All right. There are other scenarios where the other axial substituent, that might be another. So 2 things axial that are not hydrogen. But in this case, that's not the case. So here, that's not the case. So when the phenyl is axial, again, we got 1,3 diaxial interactions there. It costs 6.3 kilojoules per mole. You multiply it by 2 because there are 2 hydrogens that are interacting with that phenyl group. All right. So go ahead.
So I know there's gonna be besides the Turk beetle, I know there's gonna be 2 other like axial spots. I always get confused where they are. I think I see you numbered them, but can you go over that one more time?
Say that one more time.
So I know the Turk beetle will be axial, and I know there's 2 other spots that will also be axial. I always
Right.
get confused to where they'll be placed at.
So wherever your substituent is, count 3 carbons from it. Right. So if the substituent is at this carbon right here, right there, that's 1. So that's the site of my substituent. If you count to 3 from that carbon, you're going to end up on this carbon. So that's why your other axial site is going to be on that face. And it's the same for the other side. If I start where my substituent is and count to 3 from that substituent, you count from here 1, 2, 3, and that's where your other axial site is going to be.
Okay, would the same be for the equatorial hydrogens as well?
But yeah, but there's on every site there's an equatorial hydrogen though. That's the thing.
Okay.
Yeah. So all, even regardless of where my substituent is, all of the carbons are going to have equatorial sites. But it's just about the face, right? Because this is the bottom face, and then on the top face, your axial sites are. You can start here. You see that? That's up. And if I count to 3 from there, the next site that's up is going to be here and then here. Right, because each face has 3 axial positions.
Okay.
But the fact that they're all hydrogens, that means that there's no, right, it doesn't cost anything for those to be axial. The energy comes in and changes when you start sticking substituents on that face, or either top face or the bottom face.
Got it.
Mm-hmm. All right, so that's that. So now we can do some work. We can actually figure out how much of, let's call this isomer B and call this A. How much of B is present, how much of A is present. And we're going to just stick to room temperature. So T is 298. Kelvin. R is the same. That doesn't change. It's a constant. Hold up. On the Tia talking about my 4s, like she talked about my R's. Right, and delta G is what? It's going to be 22 minus 12.6. It's going to be 9.4. Is that right?
Yes.
Kilojoules per mole.
Is the reaction at equilibrium? No.
Yeah, the conformations are always in equilibrium with one another. It's just the extent, which one is present in a higher amount. Right, but this is an equilibrium. They can equilibrate back and forth between the two conformations, but one of the conformations is going to be present in a higher percentage than the other. So that's the extent of equilibrium. Right. So let's figure out which one is what the percentages are, the ratio. Let's figure out what the ratio is. So how do we do that?
Do find the KQ for each one, or
Now we already, yeah, we want to find KEQ period.
oh,
So we already found delta G. We know what R is. I'm just going to stick the numbers in. So that's my calculation right there. Once I know the temperature, the R is a given because it's a constant. And then delta G, I calculate by figuring out what the values are for the, well, not figuring out, but using the values for the diaxial interactions and calculating the energy for the conformation. Anybody got the number yet?
0.0225.
Okay. You said 0.022.
Yes.
All right. So that's KEQ. And if I want to get the percentage, I'm going to just take that and multiply by 100. And that's going to be 2.2. Is that right?
Yes, sir.
All right. So now that's my low number. What's the other part of that ratio? If one part of the ratio is 2.2 and it total has to be 100, then the ratio must be what? 97.8 to what? 2.2. Is that right?
Yes.
All right. So now let's go back up here. Which one is going to be the 97.8, present in 97.8%?
the second one?
Exactly.
This B, right?
Mm-hmm.
And the only reason we know that is because B is lower in energy. The energy for phenyl to be axial and for it to have those two interactions is 12.6. And this is at room temperature. And then on the other side is what? 2.2%, right? So now what I'm saying is if I took and then this is a horrible example, but if I had a Erlenmeyer flask full of cis 1-tert-butyl 4-phenyl cyclohexane, and I took a syringe and took out, you know, an aliquot, 10 milliliters or 50 milliliters or however much, 97.8% of that solution is going to be this isomer, B, and then the other 2.2% is going to be A. Like that's how this works. Both are present, but one of them is present in a higher amount than the other.
I have a question.
Go right ahead.
Looking at the chart that you gave us earlier,
Mhm.
How do you know which one will be axial, which one will be equatorial, just based off of the?
Which, oh, hold up. Which chart? Let me see.